Okay, so we're looking for the intervals of increase and decrease, the local extrema, and the intervals of concavity and inflection points. So since for A and B we're going to need the first derivative, and for C we're going to need the second derivative, so might as well just find them all right away. So the first derivative, if we get the derivative of this, we're going to get negative 2 cosine of x times sine of x, and then minus 2 cosine of x. Okay, and then if we get the second derivative, we get the derivative of this, well, here we have to use the product rule, and I'm just going to simplify it right away. We're going to get 2 sine squared of x minus 2 cosine squared of x plus 2 sine of x. Okay, so here I have my original function, the first derivative, the second derivative. Now don't forget what each one tells you. Here in the function you plug in a x value and it'll tell you the corresponding y value. In the first derivative you plug in an x value. It'll tell you the slope of the tangent line, which in other words tells you whether your original function is increasing or decreasing. And the second derivative, remember, you plug in a number and it'll tell you whether the original function is concave up or concave down. Okay, so once we have that, really A and B are part of the same process. The idea is that we're going to use the first derivative test and to find the local extrema, but at the same time we find the intervals of increase and decrease. So the very first thing we need to do is find our critical values. Those are the values at which the first derivative is either undefined or 0. So here, well, notice that the derivative, cosine x, sine x, these are continuous functions. So that means that we're only really worried about where the derivative is equal to 0. Okay, well, I notice that I can factor out a negative 2 cosine of x, and if I do that I'm going to get sine of x plus 1 left over equals to 0. And then to solve this trig equation, well, what I have is I need to solve cosine x equal to 0 and sine of x plus 1 equal to 0. Okay, so I know that cosine is equal to 0 when x is equal to pi over 2 and when x is equal to 3 pi over 2. So these are my first two critical values. Okay, and this I'm basically looking for where sine of x is equal to negative 1, which I know is equal to negative 1 when x is equal to 3 pi over 2. And notice we have an overlapping critical number. I have it 3 pi over 2 is a critical number for both of these, but that doesn't really matter very much. It's not going to change the way that I approach the problem. So I'm going to do my number line, and I forgot to state that I'm only looking for these three things on the interval from 0 to 2 pi. Because this function is actually periodic, and so it has infinitely many of the local extrema, so we only want to look from 0 to 2 pi. Okay, so I put down my critical values, which are pi over 2 and 3 pi over 2. And remember that what you do is you pick test points in each one of these intervals. And So a value that's less than pi over 2, you try to pick easy ones. So the easiest one I can think of right now is 0. Between pi over 2 and 3 pi over 2 we have pi. And between 3 pi over 2 and 2 pi would be the best one. Now you might be wondering, well, is 0 and 2 pi allowed? I mean, those are our endpoints. Well, notice that 0 and 2 pi aren't critical numbers. And they are in my interval, so they are actually allowed. And this will make the testing quite a bit easier. So remember, what we're looking for here is the intervals of increase and decrease. That means that we're going to test these values inside of the first derivative, because that's the one that tells us whether our function is increasing or decreasing. So we're going to plug in 0, and we're going to into the first derivative, and we're going to see what sign we end up with, if it's positive or negative. So we're going to have negative 2 cosine of 0 times sine of 0 minus 2 cosine of 0. And this is equal to negative 2. So this guy is negative here from 0 to pi over 2, which means that my function is going to be decreasing from 0 to pi over 2. So I'll put a big fat blue arrow right there, symbolize decreasing. Now let's test the next point, pi. So again, I'm plugging it into the first derivative. So I have negative 2 cosine of pi sine of pi minus 2 cosine of pi, and this time this is equal to positive 2, because cosine of pi is negative 1. This sine of pi is 0, so here it's going to be positive. Remember, what that tells me is that my function is going to be increasing from pi over 2 to 3 pi over 2. And last but certainly not least, we're going to plug in 2 pi and see what we get. So we have negative 2 cosine of 2 pi sine of 2 pi minus 2 cosine of 2 pi. And notice, I mean, 2 pi is basically 0, so this is going to be exactly the same value as this one, and that tells me that my function is now decreasing again. So from this I get the intervals of increase and decrease. So I can say that my function is increasing on the interval here from pi over 2 to 3 pi over 2. And it's decreasing on two different intervals, here from 0 to pi over 2, and also from 3 pi over 2 to 2 pi. Okay. But now also what follows from this is that here, see how it's decreasing and then it's increasing? Well, this means that I'm going to have a local, this is part B now, I have a local minimum at x is equal to pi over 2. Right? Because here it's decreasing, and then at pi over 2 it starts increasing, and the function is continuous at pi over 2, so that means that we have a local minimum. And to find out the y value at pi over 2, well, I would just plug pi over 2 into the original function, and if I do that, I would get, well, cosine of pi over 2 is 0, minus 2 times sine of pi over 2 is 1. So this would be that when x is equal to pi over 2, y is equal to negative 2. And also notice that we have a local maximum at x is equal to 3 pi over 2. And the reason why there is because, well, if it's increasing and then it starts decreasing, well, that's going to be a local maximum. And so, again, to find the y value at that point, you plug in 3 pi over 2 into the original function, and if you do that, you would get that y is equal to, this time, positive 2. So that's the local extrema, one local minimum and one local maximum. Okay, so now for the intervals of concavity and the inflection points. Basically what we're going to do is we're going to do exactly the same thing that we did here with the number line and the first derivative test, but we're going to do it instead with the second derivative. And so the first thing we need to do, it's going to be almost exactly the same. We're going to find they're not called critical numbers anymore, but they are possible changes in concavity. And so we're going to write down the second derivative. I'm just going to rewrite it here. And I'm going to try to find the spot, the x values for which the second derivative is equal to 0. Okay, well, remember that cosine squared is the same as 1 minus sine squared. So if I simplify this, well, what I'm going to get is 4 sine squared x plus 2 sine x minus 2 is equal to 0. Okay, and if I try to solve this, well, I can factor out a 2, and I would have 2 sine squared x plus sine of x minus 1 is equal to 0. And this is actually factorable. Here I would have 2 sine of x, and then sine of x, and then minus 1 plus 1. And so really what I would be solving is two trig equations. One is sine of x is equal to 1/2. The other one is sine of x is equal to -1. Okay, and so from this I'm going to get two possible inflection points. The first one, sine is equal to 1/2. The first value that sine is equal to 1/2 at is pi over 6. The second value that sine is equal to 1/2 at is going to be 5 pi over 6. And then here, sine of x is equal to -1 at 3 pi over 2. So all of these values are my possible inflection points. And so I'm going to do the same thing. I'm going to do a number line. I'm going to put my possible inflection points here. So I have pi over 6, 5 pi over 6, and 3 pi over 2. And I'm going to test inside each one of these. So I'm going to pick 0, pi over 2. Here I'm going to pick pi and 2 pi. And the idea is that since I'm looking this time for the concavity, what I'm going to do is I'm going to plug in these values into the second derivative, because the second derivative is the one that tells me whether my function is concave up or concave down. Okay, So let's get it started here. So I have the second derivative at 0. This is equal to 2 sine squared at 0 minus 2 cosine squared at 0 plus 2 sine of 0. Okay. Well, here these sines of 0 are 0, and so what I'm going to get is just negative 2. So what this tells me is that here my function is going to be concave down. So I'll put a upside down parabola shape to symbolize concave down. Okay. And then here at pi over 2, so let me try that one. The second derivative at pi over 2, this is equal to 2 sine squared at pi over 2 minus 2 cosine squared at pi over 2 plus 2 times sine of pi over 2. Okay, so this time what I'm going to get is, well, 2 sine of pi over 2, that's 1, times 2 is 2. Cosine of pi over 2 is 0, and then I have a plus another 2, so this is positive 4. So here I have my first change in concavity. So this means that since I went from concave down to then concave up, I'm going to have a inflection point here at pi over 6. Okay, so we're going to keep doing this for these next two intervals. Let me do it up. I'll do it right. I'll do it right here. So I'm sort of running out of room here, but that's okay. We'll make do. So what we're gonna have is now the second derivative. Now this time at pi. So this is equal to 2 times sine squared at pi, and I'm going to move it over to the next line here. I'm going to do 2 sine squared pi minus 2 cosine squared at pi plus 2 sine of pi, and here we're going to get negative 2. So that means it's negative, which means that my function is concave down, and that means that at 5 pi over 6 there's another inflection point. Okay, and our last point to check is 2 pi. And here at 2 pi, what we have is 2 sine squared of 2 pi minus 2 cosine squared at 2 pi plus 2 sine of 2 pi. And if we find that, well, these two sines are 0, so we're going to have cosine of 2 pi, so this guy's going to be negative 2. So this means that at 3 pi over 2, there is no inflection point because it's still concave down. Okay, so this means that I have two inflection points, one at pi over 6 and 1 at 5 pi over 6. So let's write this down. So those are the x values for the inflection points. But then I want to figure out the y values, and to figure out the y values, you do the same thing that we did for the local minimums and maximums. We're just going to plug these x values into our original function right here. Okay, so if we do that, what we're going to have is two inflection points. We have when x is equal to pi over 6, we have that y is going to equal negative 1/4. And when x is equal to 5 pi over 6, y is going to equal actually negative 1/4 again. So those are my two inflection points. And if you look here, you can see, I don't have enough room to write it really, but the function is concave down from 0 to pi over 6, from 5 pi over 6 to 3 pi over 2, and from 3 pi over 2 to 2 pi. And it's concave up from pi over 6 to 5 pi over 6. And that's it.